In the last episode, I talked about in general about fusion energy and general things of how we can obtain the electricity with the fusion energy. But there is also another important things to think about that many people don't talk much about that. It is the wasted that we obtain from the reaction of fusion energy. Maybe I have to do some briefly introduction about physics. I would don't talk about relativity of Einstein or quantum physics because it's awful for people listening about these things.
Preferably.
But what I wanna say that from the last episode, I'll talk about the isotopes. So the isotopes are really unstable because there are more mass of neutrons and then there are a lot of protons, so they are not stable, so they are unstable. And then instability, and that instability is the radioactive mode. So unstable elements, so anisotopes, decay usually because you want to return in a stable mode. And for this, they emit some radiation. Can be the alpha particle or the beta particle, the gamma or neutrons, to return to a stable mode. And today I don't want to talk about the relativity and also the decay period of particle, but I want to say that people have to think about that when I was talking about wastes in radioactivity, because the wastes in fusion energy or fission energy are materials that are used for obtaining electricity, but they became radioactive, and then that isotopes of materials like Pluton isotopes, 239 Pluton, and then uranium or the other things, they have to do a decay period that have not to be touched or something because they're really unstable, and for that period they can be touched and have to return in a stable mode. And when we talk about the fusion energy, usually we talk about low level wastes. So that type of isotope, they're really unstable in a first period, so they lost in a really short time their instability, so they return in the original mode in a really short time, usually minus than 1000 years. For example, the tritium used in the water to cool down the reactor is radioactive because it absorbs neutrons, and he have a period of decay of about 12 years. Is one of the shortest one. Also, there is mode to recycle this tritium really tough, because they usually how can I say, put in a storage and bring him to cool down and do his 12 years, also the uranium. So many people can ask, so if the nuclear energy is so dangerous, why we can use it? And that is the interesting part, because the nuclear energy is the better one when we think about the energy we can obtain from that. An example, 1 grams of uranium, when we do the fission nuclear, because we don't have example for fusion energy, produce the same amount of energy when we burn 2,800 kilograms of coal. And that is the interesting part. So in a sort of way, is also green more than the coal, but it's not green as we think. Returning to talk about the fusion reactors, the first generation fusion reactors have some problems when we talk about the wastes. Fine from a British team from the Professor Emma Gilbert, and they find with some simulation of the jet reactor and the demo reactor that this reactor produce some wastes, some low-level wastes, because the impurities are inside of some steels used in the wallet part of the reactor. Yes, exactly. So when we talk about impurities, we are talking about the materials used for doing a special steel, like the stainless steel, like SS 361, or the steel produced by Aerofel company. That is the company who helped the scientists to create the ITER fusion reactor in the south of France. And usually are materials like tungsten, beryllium, niobium, carbon, and also nitrogen and other ones, hydrogen and other. These are the most important ones. The first ones, like tungsten or beryllium, they have a low level of radiation and a low level of period of decay for that material. But there is the carbon and the niobium. Of course, the isotopes of carbon and niobium, like carbon 14 and niobium 94, that have a long period of decay that is over than 5,000 of year, but also they have a low level of radiotoxicity. So in a sort of way, if we're thinking of the French regulation, if we're thinking about the French regulation of radioactive elements, these carbon and these niobium are inside of low-level wastes. When we're talking about the UK regulation, they are outside.
Before we come to an end,
yeah,
I need to make a question.
Yeah.
Can we reuse the wastes of nuclear energy or nuclear centrals to produce more energy?
Yes, but in a sort of way.
Okay, but then why are we burying them?
Because for reobtain energy, recycle these wastes, or we have two options. Or we wait the decay period of the materials and then we recycle and reuse for do something. Like the steel of fusion energy have a low level wastes. So for 100 years we have to wait to recycle and reuse it. Then we can reuse the steel. An option from some experiments, they talk about that if we use the oxygen, high pressure oxygen, we can absorb or absorb in a sort of way. We can absorb the impurities of these steels, like the carbon or the niobium, that they have a high period of decay, and obtain a steel that have a short life of decay and then recycle and reuse. Or the second option is from the last fission reactors. The last fission reactors the fourth generation fission reactors, they try to reuse the wastes and products to reobtain energy. But if you want to talk about that, we will do another episode.
Oh, is that all for today?
Yeah, that's not.
Is that all for today?
No, it's not that all.
Okay.
We're not finished.
Okay, I was afraid that it was all.
No, don't worry about
please
that.
Continue.
And so maybe people say, okay, we have wastes, we have produced by nuclear energy, but how we can understand why they are low level wastes, so they are short decay period and they we can reuse in a short-term thinking, or where they are intermediate, or worse, they are high level of wastes. And there are some regulation. In the world, there is, like the banks, there is an international association that do some laws about that, but usually the countries do their own regulation for their own economy. For that they use it. And I study a little bit of UK regulation and French regulation about wastes in fusion energy, and then maybe I will talk about the Italian cause because it's really interesting, I think. And that is the UK put the limit of the wastes, of low level wastes, for about 4 megabecquerel 4 kilograms.
4 megabecquerel. What does that mean?
Yeah, it's like 4 millions of nuclides.
Oh.
So particles that go outside for 1 second of decay.
Yeah.
So 4 million particles outside of the steel for 1 second. And that is the amount when we talk about the alpha particle. When we talk about the beta and the gamma particle, the amount is a little bit different. It's like 12 megabecquerel per kilogram. These are the level to understand what is a low level wasted, what is different between a low level wasted and an intermediate one. So for obtain low level wasted from fusion energy, we have also to think about that we have to do something to catch the carbon and the niobium inside of the steel, because it can be an intermediate low level wastes, not a low level. So he has a long life of period of decay, so like 6,000 years.
6,000 years.
So 6,000. And for that, the professor Emma Gilbert think that the reactors have to build near of the reactor like a storage to put immediately the wastes here, and then start the period of quarantine of the steel to catch the carbon, to catch the niobium, and then do the geomelt period of leave the wastes in the storages around the world, like that. So there are some parts. This is the UK regulation. The UK regulations so talk about the level of decay, so the time of decay of the particle. The French regulation thinks about also the activity, so the half-life of particle, so the decay period of the particle, and also its general radiotoxicity. So for French regulation, steel with inside carbon and niobium is not as dangerous as we're thinking, because it has a low level radiotoxicity. So during a period of 100 of years, it can lose all its toxicity. Can be also radioactivity, but it lost its toxicity. So it can be reused and recycled. It's a bit strange, because country thinks of own economy and don't think about the general.
Don't think about long-term resolutions, right?
Exactly, yeah. So this is the part I wanted to talk about Italy.
Italy?
Yeah, because...
Are you Italian?
Yeah. If someone doesn't know, I am Italian. When we think about the nuclear inside of Italy, is a little bit strange, because in fact Italy abrogated the use of fusion, the nuclear energy inside of the country after the Chernobyl disasters.
No, do you find Italy's this behavior logical?
Oh, yeah, because in the 80s, the reactors were very dangerous. There are a lot of problems. Now, time has changed, and in fact, it returned in Italy the debate about using the nuclear energy. So, our Prime Minister yesterday made a speech when that is thinking about we can return to nuclear energy, but when we think about the fusion energy, not the fission energy, until the 2028. First of all, when we think about obtain energy, we have to think that if you don't want to have any wastage, you have to do nothing.
What do you mean?
That is the point.
Okay.
So every type of reaction of metal to obtain energy for humans, electricity and other things, will do some wastage. Some are more dangerous than others. Some are have to take more space than others. When we think like solar panels,
It's impossible to avoid wastes.
of course.
Okay.
And this is important. So when people think about fusion energy and fission energy are really really bad for the planet, I would say yes they are, but not as they can be. Imagine fusion energy 50 years ago was not also in the mind of the scientists. People think about nuclear energy, thinking about fission. And when we're thinking now about fission, is he did a lot. The fission energy produce a lot of wastes. They are dangerous for the planet. People have to bury it down to resolve systematically the problem. But nobody know that in the last period burn a new generation of reactors, the first generation reactors that can burn the wastes from the first part of the reaction. So the reactor produce wastes at the same time can be reused the wastes to obtain another type of energy and electrical. This is an evolution in 50 years of using the nuclear energy. So imagine what we can do with another 50 years of experience about that. And people don't have to be afraid of products and wasted. We are doing only for science, only to improve ourselves day by day to get better and better and better. Like my English. Now the first one was terrible. This one is terrible, but not like the other one. It's an improvement period. So this is the most important part. Now we produce wastes from fusion energy, low level and intermediate level. The intermediate one have to be buried to more than 50,000 years, but maybe in the next 20 years we will know how to reuse that waste and obtain energy from that, or maybe be be more safety.
The bottom line is, we just have to keep going. Dear people who listen, we'll see you